about Seyfert galaxies, quasars and blazars. The picture that we see here on the title slide is of a fairly ordinary looking spiral galaxy with a ring of dirty, dusty material around its middle. But something strange is happening in the center, and it's creating two huge lobes, bubbles, out above and below the normal plane of the galaxy. It's almost as if a jet of material is shooting out and dumping gas and dust out into these two great bubbles above and below. And this is a Seyfert galaxy. They were originally noted for being much brighter and having brighter nuclei right in the center. So what do we know about them? Well, they're strong radio sources. In fact, the image that we've got here is of the same galaxy, Centaurus A, and it's a composite picture of both optical light and radio emissions. The purple and green lobes there are the radio emissions. And they were first noted as being very, very powerful radio sources coming from somewhere in the middle of these galaxies. And it represents about 10% of all of the galaxies in the nearby part of the universe. So what we think is going on is that we have these very active galactic nuclei producing this high energy emissions and these jets that sweep out and spin around, filling these great bubbles of material above and below the galactic plane. And the theory goes that they are powered by a central supermassive black hole. So here's an artist's impression of what that supermassive black hole might look like. There's a disk of material spiraling in towards the black hole under its influence of the immensely strong gravity, being pulled in and accelerated. Friction in the disk of particles bumping into each other heats the material up to very high temperatures. I mean, we're talking 700,000 degrees Kelvin, maybe 1 million degrees, right towards the inner part of the ring. But of course, eventually the material falls down inside the black hole and vanishes and disappears. So we don't see any light from that little tiny central disk. That's where the black hole sits. But above and below the plane, we see jets of material emerging, and these are controlled by magnetic fields. The idea goes that the very fast rotation, combined with the fact that the material that's falling in at these very high temperatures is actually a fully ionized plasma of charged particles. And the magnetic field plus charged particles leads to the spiraling of the particles around the magnetic fields, and they then create their own self-magnetic field as a result of movement. And so you get a very complicated interaction that leads to these fields being twisted into a very, very narrow jet that emerges from the rotation poles, the magnetic poles of the black hole. I say emerges from the black hole, it's coming from just near the black hole, but not inside it. Nothing can come out of a black hole. The jets emerge from the accretion disk just outside the black hole. And as a result of this, we say that these black holes are like very messy eaters. Quite a large fraction of what is trying to fall in ends up being spewed out along the line of the two jets. And the particles that come out along these jets can be moving at very high speeds, up to a goodly fraction of the speed of light. In fact, our Milky Way, shown here, the horizontal plane of the Milky Way with its central bulge, and the two purple and blue lobes above and below the galactic plane are where our central supermassive black hole was feeding on material about 6 million years ago. So our very early human ancestors may have witnessed quite a light show while the black hole was feeding voraciously and creating jets out of the north and south galactic plane, which would have filled these lobes with the very hot gas that we now detect by the residual gamma ray and X-ray emissions. And in that way, our galaxy would have been a Seyfert galaxy during that period when it was erupting. And so galaxies can become Seyfert galaxies and then go quiet again. And then if more material starts to fall into the black hole, it can become active again. Now, the second type of object that we're going to talk about here is an object called a quasar. And these were discovered in the late 1950s as a result of the third Cambridge radio survey, a big survey of the radio objects in the sky. And a number of bright radio sources were found. The image here is of 3C48 in the false color picture on the right-hand side. But to begin with, there was no corresponding optical source of light associated with these bright but relatively small radio structures in the sky. What was interesting about them was that they were found to cover the whole of the sky, not constrained at all to the galactic plane of the Milky Way. And this suggested they were a very long way away, uncorrelated to our galaxy, just out there in deep space, perhaps associated with other distant galaxies. And they were given the name quasar, short for quasi-stellar radio source. The radio source is obvious, a quasi-stellar, because the more they were investigated, the more it was realized that they were very, very small indeed. So almost point-like, as is the case for stars, of course. Now, this is the Lovell telescope up at Jodrell Bank. It's a lovely picture there with the cows in the foreground. And the Lovell telescope, along with a number of others, were linked together to make a powerful interferometer, joining this radio signals from multiple dishes at different sites to get a very high resolution. And this revealed just how small these compact quasars actually were. A lucky coincidence in 1962 saw another of the most famous quasars, 3C273, go behind the moon, and the moon occulted it. An occultation is when some solar system body like the moon or a planet passes in front of a distant star or galaxy, or perhaps another planet, and blocks the light from it. And that when this happens, and it happened several times for 3C273 in 1962, the timing of the loss of signal and the known position of the moon allowed astronomers to work out very precisely on the sky where this object was. And it led to it being tracked down. Martin Schmidt used the 200-inch Paloma telescope and revealed a star-like object. You can see it on the Discovery image down there. There's a little ring around it here. So it's the tiny dot in the center. Looks like a very faint star. And that's the quasar 3C273, discovered optically for the first time. And so Martin Schmidt actually made himself quite a name for this discovery. It made it onto the front cover of Time magazine. This opened the door to studying it with optical telescopes. And the first thing that was noted was that the spectrum was very peculiar. It had a number of lines in it, but initially people couldn't recognize what the lines were trying to tell us. They normally identify the different elements that are associated with the different lines. But it turned out that they were, in fact, hydrogen, the simplest element of all. But they were shifted to the red end of the spectrum so far that people weren't recognizing the patterns. 15.8% shift in the case of 3C273. Now, a redshift like that is caused by the fact that the object is being carried away from us by the expansion of the universe, the Hubble expansion, and 15.8% for 3C273 corresponds to quite a high speed, 47,000 kilometers per second. But for 3C48, it was an even higher speed and worked out to be 37% of the speed of light. Now you can use Hubble's law, which tells us that the speed that we observe is directly related to the distance away that the object is. That's what led to the discovery that the universe was expanding. And so we can associate a distance with these objects, and these huge redshifts put them at immense distances. They were some of the most distant objects known. This particular quasar, which I won't read out its catalogue number at the top there, was proven to be 9 billion light years away. And so the light had been traveling for 2/3 of the age of the universe before it reached our cameras. Now, to be visible at such a distance, with the brightness that they have to be incredibly powerful. And of course, the other thing is that they also have to be putting out very high energy radiation, because the normal visible light will have been shifted way down into the infrared. So to see it in the visible, what we're looking at is ultraviolet or even X-rays that were emitted and have been shifted down into the visible band. It was also detected that these things were flickering and changing their brightness slightly. And rapid changes in brightness can only occur on an object smaller than a certain physical size limit. Let's just have a look at the idea for the sun for a moment. So if the sun were to change its brightness, then an effect, whatever the cause is, starting from the center of the sun's disk, can only propagate outwards and raise the brightness as a wave of information saying now would be a good time to have a flash of light, propagates across the disk at the speed of light. And so if we look at the radius of the sun, we can say that the time delay for different parts of the sun all waking up to some stimulus is going to be at least the radius divided by the speed of light. And you can do that and you get a figure of 2.3 seconds. So for the sun, a global change in brightness triggered by some event would only be able to flicker no faster than once every 2.3 seconds. Now for the quasars, we noticed that they were flickering on timescales more like hours. And so their size is light hours across. And that means that they're roughly the size of the solar system. It takes a few hours for light to travel from the sun out to the outer planets. And as observations got better, these very small, very bright, immensely powerful objects were noted to have jets. The radio astronomers and the optical astronomers both started to discover that what was really going on there was a central object firing jets out and creating two enormous radio emitter lobes, so that we were getting hot X-rays and ultraviolet light from the central region and X-rays from the two ends of the two jets. And this solved the issue of what quasars really are. They're just actually Seyfert galaxies in the early universe. They're very powerful ones, perhaps, where the supermassive black holes are feeding very voraciously, but the mechanism is in fact the same. And for the third type of object that is mentioned in the title of this talk, a blazar, actually this is just a quasar where the jet is pointing straight at us. So we're looking down the gun barrel of the jet, it's coming straight towards us. And so we see the immensely powerful, bright radiation from the jet coming straight at us rather than side on. And of course, that jet can be full of high energy particles, neutrinos, gamma rays, all sorts of things. And we've detected all of those coming from these jets all the way across large slices of the universe. Now, being so far away and so bright, these quasars sometimes line up by sheer chance with a foreground object. And this provides a great test of Einstein's theory of general relativity, his explanation for gravity. Here's a case in point. We have a foreground galaxy, a giant elliptical galaxy, that is distorting space-time around it, and 4 separate images of the distant quasar are appearing, each with a different path length, so that the light from the quasar has traveled a slightly different route and taken a slightly different time to arrive, and created 4 separate images as it's been split and bent by the curvature of space-time around the intervening galaxy. And what's interesting about this is that when we look at this in the time domain, we look at the signal changing over time, we can see that patterns of flickering in one or other of the images will occur in the next one and the next one and the fourth one at the time intervals corresponding to the different light travel times along the different lengths of path. So we know absolutely it isn't for 4 objects, it's one object, because the flickering provides a fingerprint that over time tells us that these are the same object being seen more than once. And this has enabled us to very closely test Einstein's theories. We can also use quasars to perform a CT scan of the universe. The quasar puts out its light, and as the light beam travels towards us, it goes through a number of different layers of intervening dust and gas. And every time it does so, that intervening material will stamp into the spectrum the lines for its absorption characteristics for the different elements, particularly the Lyman alpha hydrogen lines. But as the beam of light then continues on its way towards us, it's gradually getting redshifted more and more due to the expansion of the universe along its journey. And so each cloud of dust that it passes through ends up taking a bite out of it, and then those lines get shifted further and further into the red. So the most shifted ones are the ones from earliest in the journey until the nearby clouds see almost no redshift at all and are at the natural frequency of the Lyman alpha lines. And so we get a complex fingerprint. We've got 2 here, 3C273, which is at a redshift of just 0.158, which is relatively close by. And it has the classic quasar shape with a spike in the spectrum, and then a few clean lines for the Lyman alpha absorption in there. Whereas this other quasar that is much more distant with a Z of 3.62, the Lyman alpha lines are an absolute forest of information. And we've seen that it's passed through many different clouds with many different redshifts. And if we're very careful, we can decipher all of this and work out the density of the material at different distances all the way along its line of sight. And that provides an excellent way of mapping the large-scale structure of the universe, because we can do this for hundreds of different lines of sight for hundreds of different quasars. And another key fact that quasars reveal to us is that they were very common in the early universe, and nowadays we really don't see very many. This is presumably because when galaxies were forming, material was flowing around rather chaotically, and therefore tended to fall into the clutches of the supermassive black hole and feed it on a very regular basis. So a continuous flow of material leading to a very high power output for the accretion disk and the jets. But then as the universe gradually settled down, such cases have faded away, and many of the supermassive black holes now have consumed all the material that's anywhere within their grasp and become quiescent. And the importance of this is that Fred Hoyle's steady state theory predicted that the universe would be more or less the same looking at different times. The idea was that as galaxies moved apart from each other, new material would form in the gaps, and they would remain equally dense, and the universe would look more or less the same at any given epoch. Well, the story with quasars shows that that's just not right, and rather puts a nail in the coffin of the steady state theory. And another feature that we notice about the early universe, when we've done our CT scan of it, we find that there's hot gas and material along lots and lots of filaments that join up to form an immense cosmic web, many, many millions of light years along these threads of material where there's a high density of matter, and where galaxies tend to form because they condense out of this more dense regions with these huge bubble-like voids in between. And so this cosmic web has been mapped using quasars. But what we realize is that, let me just zoom this up for you, along the pathways laid out by the cosmic webs, I've marked in a lot of the Seyfert galaxies and quasars that we know about, with a little bar indicating their spin axis. That's indicating where their jets are coming out. And they are more or less aligned in most cases with the linear geometry of the cosmic web. And this is suggesting that there's a causal relationship between them. And of course, it's highly probable that the rotation of the random rotation of material leads to one predominant spin axis in various different regions of space. And it's that that creates the filamentary structure and of course leads to the dominant spin for the galaxy and the supermassive black hole, and therefore the spin axis is aligned along these threads. So a fascinating recent result, that one. Okay, well, I'll bring that talk to a close now, and thank you very much for listening.